So what we're going to talk about in this lesson is electric potential energy and electric potential difference, or just electric potential. These are terms that are very closely related to each other, so it's important that we distinguish the differences between them. Let's start off talking about electric potential energy, because if we stick with our analogy of gravity, we have gravitational potential energy, which is very similar to electric potential energy. So let's just assume we have a gravitational field, right? And let's assume that field is going down. And we want to move an object from point A up to point B. In a gravitational field, we need to apply a force to make it go that distance, right? And we can call this distance delta D. We need to apply a force over a distance to make that particle or that object move upwards in that gravitational field. And we call the amount of energy there the gravitational potential energy, right? E.g. equals mass of the object times the gravitational field strength times the change in height, or the elevation, or the delta D. We can call it, actually, yeah, let's call it delta H. I think that's what we call it with the gravitational energy equation. So there's a similar thing happening with an electric field, where we have an electric field going in one direction. And remember, we use E to signify the strength of the electric field. And if we want to take a charged particle, more specifically a positively charged particle, and we want to move that, in an electric field, the charged particle, if we just let it go, it will want to move along with the field lines. It will want to move downwards, right? So if we want to move that positive charge upwards in the field, or against the current, we're going to need to apply some force and do work to that charge, right, to get it to be up here, right? So we would call this sort of a distance that we would need to apply to that, with a certain force. The force that we're going to apply to that, in a gravitational field, the force that we're applying is m times g, right, is mass times the gravitational field strength. And in an electric field, we're going to apply the force of the electric force, which is going to be the field strength times the charge. So that's going to be the force that we apply there, and we're going to apply it over some distance. So if we think about this in terms of the work we do, the work is going to be the force times the distance. So it's just, in the case of this, if we say the work is the field strength times the charge, it's just going to be the field strength, keep saying gravitational, the field strength of the electric field times the charge times the height, or the distance we move it in that field. And we can call this, because we know work and energy are related to each other, we can call this the electric potential energy. Again, it's potential energy, just like gravitational potential energy, because of the fact that it's in a field with regards to a certain reference level, right? To a certain height above another, a starting point. So anyways, this is the equation for the electric potential energy. Notice how it's very similar. It's basically the same thing as the gravitational potential energy, right? Instead of mass, we have charge. Instead of gravitational field strength, we have electric field strength. And it's very similar. One thing to realize is that this is always, both of these equations for gravitational energy and electric potential energy are both with respect to that starting point. So you have to define that starting point, or you have to look at the energy that's gained between 2 points, like point A and point B. And that's what that delta D is. It's always the change between 2 points. So we can look at this as sort of the change in electric potential energy between those 2 points. So going down here, this is what we sort of summarized above, but let's summarize it a little bit nicer now. So in this case, we have a positive plate and a negative plate. So the field is going to be going in this direction, right? And for this, if we have a positively charged particle here, there's going to be it's going to have some electric potential energy. And you can think of that as like the energy above, this plate, because we can consider that sort of the starting point. So this would be our delta D, because it wants to go down to, that's like its rest state, is when it's at that bottom plate, at least for a proton. So we can say that that's the delta D here, if we want to just come up with like a value for the electric potential energy of that particle, right? And that's going to have some Q, some charge on that, right? And of course, the electric field has some value, some strength. So if we know that, we can determine the electric field potential, the electric potential energy, which is going to be epsilon Q delta D, right? Where epsilon is the vector there. Oh, and delta D is the vector as well, right? So you can see the higher we bring this particle up and down in the plane, the more energy it's going to have, because it's going to want to go to this negative side. It's basically like it's falling downhill, right, to that negative side. It's going to have more energy the further it is away, or the further up in the field it is. So that's electric potential energy. Not too difficult to calculate, and it's obviously measured in joules. But then we have this other term called electric potential, or electric potential difference. And you may remember from a past physics course that electric potential, or electric potential difference, is something like when you have a battery and you have a circuit, maybe with a resistor in there, and you have electrons flowing around the circuit, stuff like that. And between 2 points, we can take a voltmeter and measure this thing called electric potential difference. And electric potential difference is measured in volts, and it usually refers to how much push the electrons have in a circuit, or between 2 points in a circuit. And that's what it is. Now, the difference this here is that we're going to be looking at electric potential difference not in the case of a wire, but in the case of an electric field. And it's the same idea. If you put a particle in an electric field, the electric potential is referring to how much push that charge, or any charge at that point, has on it. So the way it's actually defined, V is the symbol we use for electric potential, because it's measured in volts. And it was discovered or formalized by Volta. The equation for that, all it is, it's the electric potential energy divided by the charge. It's the electric energy per charge. So the units for that are going to be joules per coulomb. So one way to think about it is, if you put a particle somewhere in an electric field, it's how many joules of energy that particle or that charge will have at that point in that field. That's basically what it is. And by the way, the other unit for this, a joule per coulomb, is another word for a volt, right? So the equation is, it's very, very simple. It's just basically the energy per charge. And what that does is it means it doesn't matter what the charge is. So I can have, for example, if I wanted to find the electric potential difference, the delta V, right, capital V, not small v, the electric potential difference between 2 points here, and we're looking at this charge here, the amount of charge that's here isn't going to change what the electric potential is. So this could be a 1 coulomb charge, a 2 coulomb charge, a 10 coulomb charge, and it actually doesn't matter what that is. The electric potential will be the same. It'll be some value, 10 volts or 100 volts or something like that. Whereas the energy is dependent on how much charge, because if you have more charge, that charge has more energy. So the nice thing about electric potential is that it doesn't matter how much charge you're dealing with. It just refers to, at a specific point in that field, how much electric potential energy would 1 coulomb of charge have. Okay, so it's sort of like a standard way of looking at the strength of a field throughout a field. All right, so let's do some calculations here. If the magnetic field above has a strength of 10 newtons per coulomb, determine the electric potential across the field if the plates are 4 centimeters apart. So what we know right away that the field strength is 10 newtons per coulomb, and that's going in a downwards direction as defined by, where the positive plate and where the negative plate are. So we know that that's 10 newtons per coulomb. We also know the plates are separated by 4 centimeters. So if we're trying to find the delta V of the whole plate, like between the two plates, we're looking for the delta V between the two plates, the electric potential difference between the two plates. So our delta D, our distance, is going to be 4 centimeters. And again, always put things in SI units or standard base units, 0.04 meters. So we know that. Can we determine the electric potential? Well, we know the electric potential is this. It's defined as the energy, the electric potential energy divided by the charge. So let's see if we try to do that. Let's see if we try to look at voltage as electric potential energy over charge. Well, we don't know the electric potential energy, but we have an equation for it. We have this, right? So what we could do is we could substitute that in there, right? Over Q. And what happens? You should see the charges cancel out. Because exactly as I said earlier, it doesn't actually matter what the charge is, because the electric potential difference is just telling us how strong the field is at a specific point, right? Not dependent on the amount of charge there. So to do this, all you need to do, it's basically just the field strength times the distance between them, which if we do that calculation, 10 newtons per coulomb times 0.04, so 10 newtons per coulomb times 0.04 meters gives us a value of 0.4. And the units are Newton meters per coulomb. Newton meters are a joule, so it's like a joules per coulomb, which is a volt. Basically, it's a volt. If you use all the basic units, then it's going to come out as a volt. So basically what that's telling us is that the electric potential of this whole thing, this hole between these two plates, is 0.4 volts, right? So you can almost imagine it as there's a wire going from the top to the bottom, right? And there's charges in that wire, and the difference between those two ends of the wire are 0.4 volts. So if you want to think of it sort of in terms of just wires and maybe the electricity you're a little more comfortable with, that's the way you can think about it, right? It's the same idea. So the next question is saying, determine the work required to move 1 coulomb of charge upwards at 3 centimeters in that same field. So we know when we're talking about work, we're saying how much energy is that going to gain. So we can really just use our equation for energy, for electric potential energy, to determine that. So the energy that it's going to gain is, well, just write the equation, epsilon Q times delta D. And we know the field strength. We know the charge is just 1 coulomb. We know the delta D. We're moving it upwards 3 centimeters. So we just got to plug it in. So this is what was the field strength again? 10 newtons per coulomb. So 10 newtons per coulomb. The charge is 1 coulomb. And the delta D, the amount we're moving it up by, is 3 centimeters, which is 0.03 meters. And if we do that calculation, 10 times 0.1 times 0.03 is I should have been able to do that calculation in my head, 0.03 joules. So that is the amount of work that needs to be put in to move it against the field. Remember, it wants a positive charge wants to move with the field. So by moving it upwards, we're moving it against the field. We need to apply a force, and the energy is going to be 0.03 joules. Okay, and then example 3. Determine the electric potential energy of an electron halfway between the plates. So what's going to happen if we place an electron between the plates? I don't want to muddy up that sketch up there. I'm just going to make a quick one, over here. So we know that this is the positive plate, this is the negative plate, right? If we place an electron in the middle, which way is it going to want to go? It's going to want to go this way, right? Against the field. Remember, the field is going this way. So any negatively charged particles or objects are going to want to move against the electric field. So in this case, the electron is going to want to go up. So how can we determine the electric potential of that electron? Well, it's the same thing. The reference level of this field is still this bottom point, right? That's sort of the starting point of the field. So we can say the height is still the height from the bottom, right? Which is still 2 centimeters. Well, the whole thing is 4, so halfway is going to be 2 centimeters, right? So that's our height above the bottom, but the only difference thing here is that the charge we're putting in there is going to be negative, right? So electric potential energy is equal to epsilon, which hasn't changed, times Q times delta D, which we know. So the epsilon is still 10 newtons per coulomb, and that's in a downward direction. Our Q is the charge of an electron, which is 1.60 times 10 to the negative 19 coulombs. And delta, oh, it's negative. Sorry, it's negative. The charge is negative. We just finished saying that. So yeah, we got to put in a negative 1.6 times 10 to the negative 19. And then the displacement 0.02 meters, right? And when we calculate this, we should get a small number, right? 3.2 times 10 to the negative 20, because, I mean, the charge is so small, right? And this is energy, so it's going to be in joules. So a tiny amount of energy. Oh, and it comes out negative. Sorry, I keep forgetting about the negative. Now, what does that negative mean for that amount of energy that it has? Well, the negative energy means it's not going to want to go in the direction of the field. It's a little bit weird. The potential energy wants to pull it down, right? But it actually has negative potential energy, which is telling us it wants to move upwards. So that's why there's a negative there, and it makes sense that the negative is there. That will happen whenever you have a negatively charged thing, object, particle in an electric field. It always wants to move against the field lines, okay?